The objective of this lecture is to provide insights on the transport theorem and to provide an example that demonstrates these insights. This lecture will be divided into the following parts. First, a review will be provided of the transport theorem. And this review will include an explanation of the different terms in the transport theorem and what they mean. And using this structure that we describe of the transport theorem, an example will be studied that shows how the transport theorem is used. And this example will be a simple problem that will highlight the key features of the transport theorem on a problem where it is possible to see the structure without introducing a great deal of complexity. So first, let's review the transport theorem. So recall from earlier that the transport theorem is written as follows. Given a vector B, the rate of change of B in reference frame A is related to the rate of change of B in reference frame B as dB dt in A is equal to dB dt in B plus omega BA crossed with B, where omega BA is the angular velocity of reference frame B as viewed by an observer in reference frame A. So now let's look at the transport theorem visually through a picture to provide an understanding as to what is going on with the different terms in this theorem. So recall that it is assumed that frames A and B share a point. Let this point be O. So here's frame A, and here's frame B. And there's a point O, which is common to both frame A and B. So what I mean by that is that O is fixed in A and B. O is fixed in A and B. Now I have a vector. This vector is just an arbitrary vector, B. And what's happening in the transport theorem is as follows, is that suppose we have an observer that's fixed in frame B. And I'm going to denote this observer visually as a camera. So there's a camera that's fixed to frame B. And this camera is watching this vector. And what the camera sees as the frame moves and as the vector changes is the camera sees how vector B is changing in reference to reference frame B. Here's reference frame B and here's reference frame A. So there's a camera. I'm going to call it an observer. So an observer fixed to frame B sees the vector B changing in a particular way. And this rate of change is the rate of change of B as viewed by an observer in reference frame B. But what an observer in reference frame A sees, if I fix a camera to reference frame A, now this observer is fixed in reference frame A. And the observer in reference frame A doesn't see the same thing that the observer in reference frame B sees, because frame B is moving relative to frame A. So whatever this vector B is doing, it appears to be doing something different in reference frame A from what it's doing in reference frame B. So because reference frame B moves relative to reference frame A, an observer in reference frame A sees B changing different from the change in B seen by an observer in reference frame B. So what does that mean? So that implies that the rate of change of B in reference frame A is not equal to the rate of change of B in reference frame B. And of course, I'm assuming here that the frames A and B are not the same frame. So assuming that they're not the same frame. But what is it that relates these two rates of change? So that, of course, calls into question, how do you relate these two rates of change? So the question then becomes, how is it possible to relate dB dt in B and dB dt in A? And that connection is obtained through this quantity called the angular velocity. So the answer to this is these two rates of change are connected via the angular velocity of B relative to A. Now, this is still somewhat abstract, so it is a little bit easier to be able to see this through example, and then we have to get into quantification of these rates of change using particular coordinate systems, which is what we're going to do now. So rather than continuing with the abstractness of two frames and a vector, we're actually going to use an example now to show how all of this plays out. And this example is also going to demonstrate how coordinate systems should be used when solving problems of this kind. So this example is a fairly simple problem, but it's designed to be simple because by it being simple, it makes it possible to be able to see exactly what's going on without introducing unnecessary complexity. So what we have here is we have a disk of radius r rotating on a surface. Now, I'm going to call the disk, this is my terminology, I'm going to call the disk it's going to be denoted by D, and the surface, which I'm going to call the ground, is going to be denoted by G. And this is what I'm calling the surface. This is the surface on which the disk rotates. Now I'm going to draw the picture that corresponds to this. So here is the disk. So the ground is here. And here is the disk. And I'm going to call the center of the disk O. All right. Now, in order to make this a little bit easier, O is going to be fixed in D and G. Now that's the same picture that I had earlier when I said that there's a point common to both frames. I called that point O in the abstract notion, and I had frames B and A. I'm calling it O in this example, and the two frames are now D and G. Now, I'm going to put a point Q on the end of the disk. And the distance from O to Q is R because the disk has a radius R. So next, I'm going to introduce an angle theta, and I'll explain what this angle means in just a minute. Which is the angle theta is the angle formed between the direction OQ and a direction that's fixed to the ground. So this direction right here, this direction is fixed in G. So in other words, the disk is rotating relative to the ground, and the angle theta is measuring the angle formed by a direction that's fixed in the ground and the direction OQ. Now you can see that because O and Q are both fixed to the disk, so Q is fixed to the disk, and O is also fixed to the disk. That means that as a result of that the direction along OQ is also fixed to the disk. So that means OQ itself is fixed in D, and that implies the direction from O to Q is fixed in D. And that's the starting point for this problem. So the first thing that we're going to do is we're going to set up two coordinate systems. So I'm going to draw this picture again with a little bit less obstruction, and we're going to set up two coordinate systems. So I'm going to add to this picture the following. I'm going to add two coordinate systems, or two bases. The first basis I'm going to put on this diagram is going to be the basis EX, EY, and then EZ. And I'll define what all these directions are. Now we said that the angle theta is measured from a direction fixed to the ground to the direction OQ, where Q is fixed to the disk. So EX is the EX, EY, EZ is this basis that I've just defined. The coordinate system has its origin at point O. So this is going to be a ground fixed coordinate system. So this has its origin at O, and then EX is going to be equal to along, now I have to be careful, it's along OQ when theta equals 0. So of course theta changes with time because the disk is rotating relative to the ground. So theta is a function of t. I didn't actually say theta is a function of t, but it's not constant, so it's changing with time. And then EZ is the direction out of the page. And then EY is equal to EZ crossed with EX. Now this coordinate system is fixed in G. Now what I'm going to do with this is as follows, is before I introduce my second coordinate system, because I am going to introduce a second coordinate system, let's express the position of Q relative to O. So here's what we're after in this problem. So the objective is determine the rate of change of the position of Q relative to O as viewed by an observer fixed in D and G. Now, the first thing that we can see here is because O and Q are fixed in D, we know that the position of Q relative to O is also fixed in D. So what that means is the position of Q relative to O is fixed in D, which implies that the rate of change as viewed by an observer fixed to the disk of the position of Q relative to O has to be 0 because, as noted from the earlier material, that any vector that's fixed in a frame, its rate of change in that frame has to be 0. And so this last result is because the rate of change of a vector relative to a frame A is 0 if that vector is fixed in frame A. So we know now that the rate of change of this vector as viewed by an observer fixed to the disk is 0. Note, however, that the rate of change in G of the position of Q relative to O is not equal to 0 because Q is not fixed in G. Now, one way to do this, which is not the correct way or not a good way to do this, is to just naively work with this basis, EX, EY, EZ. So we can do that. So first, start by solving for the rate of change in G of the position of Q relative to O using the basis EX, EY, EZ. If we do that, we wind up with the following. So first, we know that the picture would look as follows. We have EX, EY, And we have this position of Q relative to O. And then we have this angle theta, and this distance here is R. So from this information, we know that the position of Q relative to O, it has two components. It has a component of R cosine theta in the EX direction plus R times the sine of theta in the EY direction. Now remember that this basis, EX, EY, EZ, is fixed in G. So as a result, we can take the rate of change of this vector that we have here, the position of Q relative to O, as follows. So then, because R is constant, it's the radius of a circular disk, and EX and EY are fixed in G, we have that the rate of change in G of the position of Q relative to O is just going to equal d dt of R cosine theta times EX plus d dt of R sine theta EY. I haven't factored out the R yet, but R is constant. And the reason that it's simply equal to what I have here in the last expression is because these two vectors, EX and EY, are fixed in G. And as a result, that means that dEx dt in G is equal to dEy dt in G, which is equal to 0. So I would have a product rule. I'd have the derivative of the first times the second plus the first times the derivative of the second, but there is no product rule in this case because these basis vectors, EX and EY, are fixed in G. So as a result, I can now write that the rate of change in G of the position of Q relative to O is equal to, well, as I said, R is constant. So I just get R times d dt of cosine of theta times EX plus R times d dt of sine of theta times EY, which is equal to R. Now I have to be careful because I'm taking the derivative with respect to time. So the derivative of cosine theta with respect to theta is minus the sine of theta. So I get a minus sine of theta, but then it's times d theta dt. So I get minus R theta dot times the sine of theta times EX. Similarly, the derivative with respect to time of sine theta is cosine theta times theta dot. So I get plus R theta dot times the cosine of theta times EY. Now this quantity I'm going to call the velocity of point Q in G. This is the velocity of Q as viewed by an observer fixed in G. Now you can see that when I did that, I used purely the basis EX, EY, EZ, which is fixed in the ground. But that's not the best way to do this problem. It is a way to do this problem, but it's not the best way to do this problem. There's a much better way which takes advantage of the geometry. So now we're going to actually go back and we're going to take advantage of the geometry. So now let's add to the picture. So we're going to add to the picture a second basis. Now this basis is actually going to be fixed in the disk. I'm going to put a direction, I'm going to call that direction UR. And UR is going to be along OQ. I'll define all these below. UR is along OQ, and I'm going to define a direction UZ, which is actually out of the page, which is in the same direction as EZ. And then I'm going to define the cross product, which is going to be U theta, which is going to equal UZ crossed with UR. It completes the right-handed system. So now let's define this coordinate system. So I have the origin of this coordinate system at O. I have UR, which is along OQ. I have UZ, which is equal to EZ, and I already defined EZ. And I have U theta, which is equal to UZ crossed with UR. This coordinate system is fixed in D. Remember that OQ is fixed in D, so the direction along OQ is also fixed in D. Now, UZ is also fixed in D because its direction doesn't change relative to the disk, and it's equal to EZ in this particular case. Those two things happen to equal each other. And then U theta is UZ crossed with UR, and because UR is fixed in D, U theta also has to be fixed in D. So now you can see that when I do it this way, I can actually express the position of Q relative to O much more easily than I could have when I used the basis that was fixed in the ground. So let's do that now. So then, in terms of the basis, UR, U theta, UZ, the position of Q relative to O can be written as, or can be expressed as, the position of Q relative to O is equal to R times UR. Now you see that that's a much simpler expression from what we had before. It is equal to the expression we had before. What we had before was R cosine theta EX plus R sine theta EY. They are indeed equal to each other. But this expression, you can see, is much easier to write than the other expression. Now, not only is it easier to write, but now we can actually figure out the rate of change of the position of Q relative to O as viewed by an observer fixed to the ground, but now we have to use the transport theorem. Why do we have to use the transport theorem? Because we want the rate of change of the position of Q relative to O as viewed by an observer fixed to the ground, but we are expressing this position in terms of a basis that's fixed to the disk. So let's write that out in words. It says we want the rate of change as viewed by an observer fixed to the ground of the position of Q relative to O. Now, in this case, RQ relative to O is expressed in coordinates fixed in D, but it is desired to obtain the rate of change of the position of Q relative to O as viewed by an observer fixed in G. So as a result of the fact that we have expressed the vector in terms of coordinates fixed in D, and we want the rate of change as viewed by an observer fixed in G, we need to apply the transport theorem. So that implies that the rate of change in G of the position of Q relative to O has to equal the rate of change in D of the position of Q relative to O plus the angular velocity of D in G crossed with the position of Q relative to O. That's the transport theorem. Now you notice that in all three slots, the same vector appears. It's the position of Q relative to O because that's the vector whose rate of change we're trying to compute. Now we already know that the rate of change in D of the position of Q relative to O is 0. So we're going to start there. So we already know that the rate of change in D of the position of Q relative to O is 0 because the position of Q relative to O is fixed in D. So that first term in the transport theorem in this particular case is 0. So the next thing we need to compute the angular velocity of D in G. Now, let's go back to the diagram. So the diagram, now we can add to this diagram that basis UR, U theta, UZ. So there's UR, there's U theta, and then here's UZ. This angle is theta. Now, let's be really clear about this. We know that EX, EY, EZ is fixed in G. We know that UR, U theta, UZ is fixed in D. And this angle represents the angle between that direction EX, which is fixed in G, and the direction UR, which is fixed in D. So as a result, this angle leads to the angular velocity of D in G equaling theta dot times UZ. So what are these things? So let's go into even a little bit more detail so we can understand what all these things mean. So we have omega dg is equal to theta dot times uz. Now this quantity right here, this is the rate of rotation of D relative to G. This quantity right here is the direction of rotation. Now the direction of the rotation of D relative to G. Now that direction of rotation, it's really important that it's understood that the plane of rotation is the EX, EY, or UR, U theta plane. But the axis of rotation is orthogonal to that plane. So if you curl your fingers in the direction of the rotation, your thumb will point in the direction of the axis of rotation, and that axis of rotation is UZ. So now we have everything we need to apply the transport theorem. So we recall that the rate of change in G of the position of Q relative to O is equal to the rate of change in D of the position of Q relative to O plus the angular velocity of D in G crossed with the position of Q relative to O. And this quantity right here we already know is equal to 0. So that only leaves these two quantities. So that means that we have 0 plus theta dot uz crossed with RUR, which is equal to R theta dot U theta, which implies that the velocity of point Q as viewed by an observer fixed in G is equal to R theta dot U theta, because this velocity is equal to that rate of change. Now, let's look at the two expressions that we have. So we have that the velocity of point Q as viewed by an observer fixed to the ground is equal to minus R theta dot sine theta EX plus R theta dot cosine theta EY. And that's when we used the basis that was fixed to the ground. But when we use the basis that's fixed to the disk, we get R theta dot U theta. Now look at these two expressions. You can see that the first expression is more complicated than the second expression. In addition, the algebra that was required to get the first expression is more complicated because we had to actually take a derivative, we had to use the chain rule, we had to do all these things, and we had to work with sines and cosines. In the second expression, we didn't have to do any of that. So the second expression, the reason it comes out the way it does is because it conforms much better to the geometry of the problem. And here's what I mean when I say that it conforms to the geometry. So recall the diagram that we drew earlier. Here's that diagram. Now you'll notice that the direction of the velocity of point Q is in the same direction as u theta. If I draw this, that direction is along u theta. Now I'm going to try to get this as close to parallel as possible. But this is the velocity of point Q in G. And the velocity of point Q in G is in the direction u theta. And you'll notice that u theta is tangent to the circle. And that would make sense because this is circular motion. So as a result, you would expect that velocity to be tangent to the circle. So it's consistent with the geometry. It also winds up giving you a much simpler expression from what you would have gotten had you done this using the basis that was fixed in the ground. So using coordinates that are fixed in the disk gives you the advantage of being able to take advantage of the geometry. So once again, I'm going to remind everyone that this basis is fixed in G, and this basis is fixed in D. Now, I'm not going to go through getting the second derivative or the acceleration using these coordinates that are fixed in the ground because it's not a good way to do it. And you can see that when you have to take this derivative again, if you use coordinates that are fixed in the ground, this is going to become an even more complicated expression because now you have a product that you have to deal with. It's theta dot sine theta, and you got another product, theta dot cosine theta, and you have to take the derivative of that with respect to time. That's going to be a very difficult and very mistake-prone process. But we are going to actually compute the second derivative again using the transport theorem, and we'll do that now. So suppose now that it is desired to obtain the rate of change in the ground of the velocity of point Q as viewed by an observer fixed to the ground. This quantity happens to equal the acceleration of point Q as viewed by an observer fixed to the ground. So that's the acceleration of Q as viewed by an observer fixed in G. But now let's start again with the velocity of point Q as viewed by an observer fixed to the ground. So recall the velocity of point Q in G is equal to r theta dot u theta. Now, notice that this is expressed in coordinates fixed in D. But we want the rate of change in the ground of the velocity of point Q as viewed by an observer fixed to the ground. So because the original expression here, the derived expression, velocity of point Q as viewed by an observer fixed to the ground, is expressed in coordinates fixed in D, and we want the rate of change as viewed by an observer fixed to the ground of that velocity of point Q in G, we need to apply the transport theorem. So we need to apply the transport theorem. Now, how are we going to apply the transport theorem in this particular case? So let's see how this works. So we then have the rate of change in the ground of the velocity of point Q as viewed by an observer fixed to the ground has to equal the rate of change in the disk of the velocity of point Q as viewed by an observer fixed to the ground plus the angular velocity of the disk in the ground crossed with the velocity of point Q as viewed by an observer fixed to the ground. This time we're taking the rate of change of V, Q, and G. So as a result, in all three of these slots is the same vector, the velocity of point Q, as viewed by an observer fixed to the ground. But in this case, it's a little more complicated because this first term in the transport theorem is not zero. So let's look at it. D dt in D of the velocity of point Q in G. Well, we recall that the velocity of point Q in G is equal to r theta dot u theta. But r we know is constant, and theta is changing with time, but u theta is fixed in D. So the only thing in this expression that changes when viewed from the perspective of the disk is that the angle theta is changing because r is fixed is a constant and u theta is fixed in D. So as a result, this rate of change becomes r theta double dot u theta because again, r is constant and u theta is fixed in D. So the only thing that's changing from the perspective of an observer fixed in the disk is the angle theta. Now the next term is a cross product. And that cross product is omega dg crossed with the velocity of point Q in G, which is equal to theta dot uz crossed with r theta dot u theta. So I just substituted in the expressions. That's all I did. Now, if you look, you'll see that the r theta dot can be moved out front, and so you just get uz crossed with u theta. Well, uz is the third basis vector, and u theta is the second basis vector. So the third basis vector crossed with the second basis vector is minus the first basis vector. So this is equal to minus r theta dot squared times ur. And now all we have to do is just add these terms together. So we get that d dt in G of the velocity of point Q in G is equal to r theta double dot u theta minus r theta dot squared ur. But this is out of order because the basis order is ur, u theta, uz. So we put it back in the order of the basis, and we get minus r theta dot squared ur plus r theta double dot u theta. And as I said, this quantity is equal to the acceleration of point Q as viewed by an observer fixed to the ground. So now we've applied the transport theorem twice. The first time we applied the transport theorem on the position of Q relative to O, and we got the velocity of point Q in G, and that was r theta dot u theta. We then took the rate of change of that as viewed by an observer fixed to the ground, and we got the acceleration of point Q as viewed by an observer fixed to the ground. So this example provides quite a bit of structure with regard to how the transport theorem actually works, and it actually shows you that using an appropriate basis or observation, if you want to call it that, in this case the observations that are the most useful are the ones from the perspective of the disk. And as a result, we can write these rates of change in a nice compact way that makes it possible to express things in a way that takes advantage of the geometry of the problem. That's the key thing, is that it takes advantage of the geometry. So that takes us to the end of this particular lecture. So in this lecture, to summarize, we first studied the transport theorem in more detail, and that allowed us to explain what each of the terms in the transport theorem meant. And then after studying the transport theorem in a little bit more detail, we provide an example to gain insight into the structure of the transport theorem. And that takes us to the end of this lecture. And this example hopefully will be something that can be revisited from time to time when perhaps it gets a little bit confusing to understand what's going on with the transport theorem. But in this particular case, we have a way of being able to bring it down to something as simple as possible in order to understand what all these different pieces in the transport theorem mean. And we'll end this lecture at this point.